Okay, BC Kids, we're looking at section 10.6, which is the comparison tests for convergence. There's two tests. There's one that's called the direct comparison test, and there's one that's called the limit comparison test. And so we're going to look at the direct comparison test first. They just call it the comparison test. We're going to refer to it as the direct comparison, just so there's a difference between the two. All right. The thing with this guy is that once you have decided convergence for your comparison, you need to check this inequality. So this is really important. For this one, this direct comparison, you have to check the inequality. I'll show you what I mean in a minute. All right, so where's the inequality? This is the inequality right here. A sub n is your original summation, and B sub n is what you're using to compare it to. And so you have to make sure that it's a value, your B sub n is something that is bigger than what A sub n is. And if it is, then you can decide if B sub n converges, then A sub n converges. And if A sub n diverges, then B sub n diverges also. Okay, so let's try a couple problems. What do you mean compare? And here's what I mean. I'm going to look at the fraction I'm given. This is my A sub n fraction, and I've got to figure out something that I want to compare it to. And what I want to compare it to, obviously, is going to be something a little simpler than what this actually is. So if I'm looking at this, I have 1 over 3 plus 2 to the n, and in thinking about that, 2 to the n is really the decider of what this looks like. This 3 plus doesn't really matter much. And so I'm kind of zeroing in, I'm eyeing in, and I think what I'm going to use to compare is 1 over 2 to the n. Do you see how the behavior of 1 over 2 to the n would be extremely similar to this? The only difference is that you're adding 3. And so if I'm comparing it, now I know that this is a geometric series. Can I write it as a geometric series? And you say, yep, you can. It would be n equals 1 to infinity, and it would be written as 1 over 2 to the nth power, right? 1 over n, 1 to the n, 2 to the n, 1 over 2 to the nth power. Well, according to geometric series, your r is 1/2, and 1/2 is, it's absolutely the actual value of 1/2 is less than 1. And so since your value, your r, is less than 1, we know that this converges. Well, if it converges, then we know what the value of our comparison, our original, this is the comparison, it converges. So this would also converge provided that the inequality is correct. So let's go to the inequality. 0 is less than A sub n, 1 over 3 plus 2 to the n is less than 1 over 2 to the n. If that's a true statement, then I know that by comparison, my A sub n is also going to converge. So let's think about it for a minute. Say I have 2 to the third, 1/8. Is 1/11 smaller than 1/8? And the answer is yes, so my comparison would work, and I can say, therefore, the summation of my A sub n, 1 over 3 plus 2 to the n, converges by the comparison test, direct comparison test, depending on the book. But that's that guy. Okay, so let's try another one. This time, what do you think I'm going to compare it to? And you can kind of tell because it's a similar problem to the last one. By the way, you need to exactly say what you're comparing it to. You can't just leave it up for for grabs. You need to write down exactly what you're comparing it to. So this one's going to be compared to 1 over 4 to the n for the same kind of reason. Well, we know that that's a geometric series test, and so if I put it together, I know that the sum for this guy, and 1 to infinity, of 1 over 4 to the nth power is going to be the same kind of thing as what I did in the last problem. My r is 1/4, and I know 1/4 is less than 1, therefore this guy converges by the geometric series test. Let's check our inequality. So if I have 0 is less than my a sub n is less than my b sub n, I have, let's put in a 2. 1/16 is 1/16 bigger than 1/13. Ooh, think on that one. 1/13 versus 1/16. This is not true. Well, that means that I can't make a conclusion right now based off of this because it doesn't work correctly in my situation here. So let's try something else. If I think of 1/4 to the nth power, and I want to use the comparison test, this didn't give me what I wanted to have because this inequality is not true. So I'm going to make a new comparison. I'm going to try again. And here's what I'm going to use. 1 over 4 to the nth power, is that somewhat similar in behavior to 1 over 3 to the nth power? You try to stay close, like you're not going to pick 1 over 2, you're going to stay close to 1/4. But they would have similarities, right? If I look at them, their flow is going to be about the same. If I were to graph them, they're going to be very similar in nature. So that's what I'm going to try this time and see if that makes a difference. Well, we're still going to try the geometric series test on it. All right, let's see, equals n equal. By the way, you're not always using the geometric series test, but for these two it worked. 1 over 3 to the n, which means my r is the absolute value of 1/3 less than 1, so it converges. All right, let's check our inequality. Now our inequality would be 0 is less than a sub n, 4 to the n minus 3 is less than my comparison. Let's see if that works. So if I have, again, a power of, this is a power of n here. If I have a power of 2, this is 16 minus 3 is 13, 1/13 compared to 1/9. And that works. That is true statement. That is going to be a true inequality. So that means that, therefore, by comparison, my original summation here, 1 to infinity of 1 over 4 to the n minus 3, also converges. So again, you got to check this inequality, and I would say by comparison test. All right, last one on comparison test, and then we're going to try a different type of test, which is really a lot more popular. This is not the most popular of tests because you've got to make this inequality work, make sure that it works in order for the comparison to be made. All right, so now I'm looking, I have 1 over 7n squared plus 4, and I'm going to think about what I'm going to compare it to. And so you kind of, there's a video I think I showed you that you kind of squint. You kind of squint at this thing. You squint and you kind of look at what's the basic function that you've got going on here. And really it's 1 over n squared. 1 over n squared is going to behave the same or similarly to 1 over 7n squared plus 4. All right, so I'm going to compare it to 1 over n squared. Well, that's nice because that guy then is a p-series, right? This is a p-series. And I know my power is 2. And if my power is greater than 1, according to the p-series, it converges. By p-series. Well, I kind of said that in the front, didn't I? So I know that my first one, 1 over n squared, is a converging p-series. So now I got to check my inequality. Check the inequality. Is 0 less than a sub n, 1 over 7n squared plus 4, less than 1 over n squared? Let's use a 2. Check it out. 2 squared is 4. 4 times 7 is 28. The 1 over 32. Is 1 over 32 smaller than 1/4? And we say yes, yes it is. And so this is true. And so since it's true, I therefore know that my series I was really trying to work with also converges by the direct comparison test. Direct comparison test. Okay. There it is. So there's direct comparison test. And again, the big deal is you've got to check the inequality and make sure that it works, that a sub n is less than b sub n. So the next one's this limit comparison test. And the limit comparison test is definitely a lot more popular. So there's a couple things that come into play with this. On my highlighter here. If a sub n is positive and b sub n is positive, then the limit of a sub n divided by b sub n is equal to some number where that number is finite and positive. And if that happens, then both a sub n and b sub n converge, or both a sub n and b sub n diverge. So here's what I'm putting here to finish this out. Either both converge or both diverge. All right, now here's the nice thing about this guy, this limit comparison test. No need to check an inequality. Okay? So there's no need to check that in the midst of this, which makes it kind of nice, which is why a lot of people like it better. All right, let's try some more problems, examples. There's lots of practice problems, or lots of example problems this time around. Here we go. So let me show you how this one works. I'm going to use the limit comparison test for these guys. There's Levi. He sounds so vicious, but he's so sweet. As soon as one dog in the neighborhood goes off, he goes off too. All right. So here's what I'm going to do for this one. I'm going to think about, and again, I'm going to kind of squint. Let me close the door. Hang on. That'll help a little bit. All right, so I'm going to kind of squint and figure out what's the major function going on here. I have a highest power of n squared in the top, and I have a highest power of n to the 5th on the bottom. Don't really care about the coefficients again, and I really don't care about the whole rest of this. So if I'm thinking about, I'm still going to figure out what I'm comparing it to. I'm going to compare it to 1 over n cubed. Because 1 over n cubed is going to behave the same way, similarly to the 5n squared, 2 times n squared, and the 5n to the 5th on the bottom. All right, so let's think about this. If I compare it to 1 over n to the 3rd, then for this one, I know that 1 over n to the 3rd is a p-series. Going to think about what my comparison guy does. He's a p-series. He's a power of 3, which is greater than 1. And if that happens, then I know that this converges by the p-series. Again, I don't need to do I don't need to do an inequality with this. So now what I'm going to do is I'm going to compare that, and I'm going to put it in here into my limit comparison test. Well, the limit comparison test says this: the limit as n approaches infinity of my original function, and I'm going back and looking at, just where this is coming from, right here. So I have to take a sub n, what the original one is, and divide it by what I'm comparing it to. All right, so that's where I'm getting this from. So I'm going to take a sub n, that's this whole big crazy original thing, 2n squared minus 2 over 5n to the 5th plus 3n squared plus 1. And I have to divide it by 1 over n cubed. Now, think algebraically about that. If I'm dividing by 1 over n cubed, I'm really multiplying by n cubed over 1. You know, keep, change, flip-ish type thing. And then what I want you to do is think about what this is like a horizontal asymptote. If I'm thinking about what a horizontal asymptote would be, I'm going to put a little ha out here because that's what I'm thinking. Then the power on top, if I'm looking at this, if I'm looking at the main stuff here, I have, I'll put an arrow, I have a 2n to the 5th is my biggest thing, and I don't care about really the rest of this. And on the bottom I have a 5n to the 5th. And if I'm thinking about horizontal asymptotes, then they're the same powers, and so my limit is going to equal, maybe I just want to go this way instead of rewriting the whole thing all over again. Maybe I just want to go into the next box just slightly. If I look at this, it's really 2/5, right? So now I have an answer of 2/5. If I look at my 2/5, there's two requirements for it. One of them is that it has to be finite, and one of them is that it has to be positive. And if I look at that, it is finite and positive. And so I can say, therefore, this one also converges. So, wait a minute, I want to get my writing right here. So, the sum going from n equals 1 to infinity of 2n squared minus 2 over 5n to the 5th plus 3n plus 1 also converges by the limit comparison test. So what you're going to do, and you go back to the box, make sure that we answer what we're supposed to answer. If I'm looking at this box, if I have my a sub n divided by b sub n, it has to come out to be some number, and that number has to be finite and positive. Means that they both converge or they both diverge when I make that comparison. And so we've done all the requirements. We're good to go on number 4. Number 5. Job number 1 is, what am I going to compare it to? For number 5, there it is. Number 5, I'm going to compare it to, I have an n squared power on the bottom, I've got a 1 on top, 1 over n squared. Well, a lot like the last one. I have 1 over n squared is a p series where the power is 2, 2 is greater than 1, and therefore I know that that converges. All right, let's do the limit comparison test. The limit as n approaches infinity for, let's do the division, 1 over 5n squared plus 5n plus 5 times, keep, change, flip, n squared over 1. So really what I'm looking at, again, thinking about horizontal asymptotes, is this guy right here over this guy right here. Well, what is that limit going to equal? And we know that it's going to equal 1/5. And then we ask ourselves, is that 1/5 positive? And is it finite? And we say, yup, it is. And so I can say, therefore, my original summation here, n equals 1 to infinity of 1 over 5n squared plus 5n plus 5, also converges by the limit comparison test. Now, are they all going to converge? Because so far it seems like they're all using p-series and they're all converging here, and the answer is nope. All right, so let's try another. Number 6. I am looking at 1 over the square root of 3n plus 2. Well, again, if you kind of eye in on what the main simplest function that would be comparable to that, comparable, I would pick, I'm talking and trying to write at the same time, isn't working. Compare 2, 1 over the square root of n. Right, because that's really what it is. It's 1 over a square root. So I'm going to compare it to 1 over the square root of n, and I can still use my p-series. But now my power is a square root. Well, what's the power of square root? It's like a 1/2 power, and 1/2 is now less than 1. And so by the p-series test, I know that this diverges. Well, that's interesting. Let's try the limit comparison test and see what it does. The limit as n approaches infinity for 1 over the square root of 3n plus 2 divided by times the square root of n over 1. And again, I'm really just looking at the main parts of this thing that are controlling what this is going to do. And so if I look at that, I'm going to end up with evaluating. Now again, you're talking horizontal asymptotes. The powers are the same, so it's the coefficients when you look at the limit. And so it's going to be 1, or actually I guess I should leave it as the square root of 1 over the square root of 3. But we all know that the square root of 1 is 1, so it's really 1 over the square root of 3. Now, is that positive, and is that finite? And the answer is yes. And so, therefore, I know that the sum I was really trying to get to, 1 to infinity of 1 over the square root of 3n plus 2, also diverges. So they either are both going to converge or both diverge, but you're using this limit comparison test to do it by the limit comparison test. All right, a couple more. This one, if I want to compare, again, I've got ugly functions going on here. That's like just really weird, but I'm going to compare it to an n cubed over an n to the 5th. I'm going to do an 1 over n squared. Well, we did that just a second ago up here right above it. So it's a p-series. P-series. And the p-series has a power of 2. 2 is greater than 1, and therefore this one converges by the b-series. And so I'm going to do my limit comparison test, see what happens. Limit as n approaches infinity of, holy moly, n cubed minus 7 over 2n to the 5th plus n squared plus n plus 1 times n squared over 1, which gives me an n to the 5th on top, and it gives me a 2n to the 5th on the bottom. So what I'm comparing, or what I'm figuring out my horizontal asymptote, these guys become n to the 5th, and I have it over a 2n to the 5th, which means that my horizontal asymptote, my limit, is going to be 1/2. Well, 1/2 is positive and finite, and since this converged, then this guy's going to converge too. So my sum of n cubed minus 7 over 2n to the 5th plus n squared plus n plus 1 also converges by the limit comparison test. There's number 7. Number 8, we're motoring along. All All right, this one's going to be a little different. This one's not a p-series anymore. So if I'm looking at number 8, do you see how this one's different? This one doesn't have just a constant on the top, so I can't quite use what I've used before. It's got this crazy n that's being multiplied by it. So if I look at this one, the thing that comes to mind is maybe the very first test that we did. Let me see if I can try the nth term test, but I still need to figure out what am I comparing this to. If I look at it and I kind of, again, squint in on it, compare to, this is an n, this is a 4n cubed, so that would be an n squared on the bottom, right? An n over an n cubed. But this still has 3 to the n that's generating terms. So that's what I need to compare it to, is this 3 to the n over n squared. And I'm thinking of the nth term test, one of our very first tests that we looked at, which means I need to take the limit as n approaches infinity, and I'm going to take that with this 3 to the n over n squared. And the whole deal with the nth term test is, does it equal 0 or not, kind of thing. So if I'm looking at this and I'm thinking about which part is growing faster, is the 3 to the n growing faster or the n squared growing faster? And it turns out the 3 to the n is the part that's growing faster, which means that this is not going to equal 0. Think about it. If I have 3 squared, that's 9. Over 4, 27 over 3 squared, 9. So like you can see that the top is growing faster than the bottom is growing, so it's not going to equal 0. And the nth term test says, okay, well then it diverges. You can go back and check your chart for the details of the nth term test. But anyway, that's the truth. If it doesn't equal 0, it diverges. So now I can apply. I really want to know what this guy's doing. So I used my comparison test. I decided that this guy diverges. So if I take the limit as n approaches infinity for my guy, n times 3 to the n over 4n cubed plus 2 times, now I'm going to flip this, right? Keep, change, flip. N squared over 3 to the n. There are some things that cancel out and make it kind of nice, right? So if I look at this, I've got a 3 to the n up top, I have a 3 to the n on the bottom. They can cancel each other out. And then what I have is, if I combine this together, I have an n cubed up top and a 4n cubed plus 2 on the bottom, which makes it pretty easy for me to see what that limit is actually going to equal, and that would be 1/4. And since 1/4 is positive and finite, I know that my original, can you still see me? Yeah. My original n, 3 to the n over 4n cubed plus 2 also diverges by the limit comparison test. Okay. So there's one that's just slightly different than some of the others. I'm going to go with number 9. Number 9 is back to the same old stuff we've been doing. This one is back to a p-series. All right, so I've got to think about this. I'm going to compare it to, it's always like, what are you comparing it to? So it's n over, this would be n to the 3/2, right? The square root of an n cubed, n to the 3/2 power. If I have n to the first over n to the 3/2, I would have n to the 1/2 when I subtract those powers. So that's what I'm going to compare it to. All right, well, let's go to p-series again. My lovely p-series, love them. I have 1/2, and 1/2 is less than 1, and since it's less than, that means that this guy diverges by the p-series. Okay? All right, so I know then what the limit comparison test is going to be. If it comes out positive and finite, it's going to do the same thing. Let's check it. The limit as n approaches infinity for n over the square root of n cubed plus n times, this is n, the square root of n over 1. Well, kind of strange. But I know up here I have n to the first times n to the 1/2. Add the exponents, it's n to the 3/2. What's the power down here? He's an n to the 3/2. Plus yada yada, I don't really care. These guys are the same powers, so I take their coefficients. So this limit equals 1. Well, is 1 positive and finite? And the answer is yes. And so I know that my sum, 1 to infinity of n over the square root of n cubed plus n, also diverges by the limit comparison test. All right, I'm just going to do a couple problems because this one's getting a little long. I want to pick number 3 was my first one that I chose. This one says use the comparison test. Well, that's the first one that we talked about, which means I need to check the inequality. So you got to figure out which test you're looking for. If they don't give you any statements, then go for the limit comparison test because it just is a little nicer. But for this whole section, the deal is, what am I comparing it to? So I'm going to compare to, let's see, 1 over, here, this is the guy that's controlling the whole thing, 1 over 5 to the n. If I compare it to that, then I can use the geometric series test. And I can see that that would be like the sum of 1/5 to the nth power, my comparison guy. Well, that means that r equals 1/5, and 1/5 is less than 1, there, the absolute value of that. Therefore, this guy converges by the geometric series test. All right, we have to check the inequality for this one and see, is it true? I did my inequalities the last time in orange, so let me go orange. Is 0 less than 1 over my a sub n, 1 over 2 plus 5 to the n, less than my b sub n, 1 over 5 to the n? Check the inequality, put in a 2. I have 25 plus 2 is 27. Is 1/27 smaller than 1/25? And the answer is yes. That means that I did well, and I know that these both converge. So I can say that my original a sub n, 1 over 2 plus 5 to the n, also converges by the direct comparison test, or just the comparison test as they call it. Okay, so just a reminder of how that one works. There's a little bit of numbers 5 and 6. Be careful of, this is that whole comparison thing. Do they converge? Do they diverge? And it's all based off of the inequality that's in your box that says 0 has to be less than a sub n, has to be less than b sub n in order for them to both converge or diverge. So just beware of that for answers 5 and 6. We can talk more in class about that if you have questions. The other one I chose was 14 because 14 is set up a little different than the rest of these. Most of these are very similar to the examples we've done together. But 14, they give it to you in a different form. See how 14 is a little bit funky? So, but they tell you, consider here this series, and then they give you the summation, and they say use the limit comparison test with the series. They're telling you what to compare it to determine the convergence of these series. All right, well, if I'm looking at this guy, I'm going to start with the comparison, right? N equals 1 to infinity of 1 over 4n. I would compare, or I would think about that as behaving the same as 1 over n. Right? Wouldn't that be very similar? 4 times it, it's going to have this similarities in the way that it is behaving, because the 4 just makes it go faster. But 1 over n gives you harmonic, remember him, he's a harmonic series, and I know he diverges. Any harmonic series is going to diverge. We talked about that in class. So then it says, okay, we'll use the limit comparison test and see what it does. Well, the limit comparison test says take the limit of 1 over 4n minus 3 times this guy, what I'm supposed to be comparing it with. 4n over 1, keep, change, flip, I'm dividing by that. Think about your limits. You have a 4n on the top, you have a 4n on the bottom, n and n. So take their coefficients, 4 over 4, that equals 1. And so since it is positive and finite, then I know that they both, therefore both, diverge. Diverge. Let me make sure that was the end. Could be the end. And it is. Okay, so there you go. The direct comparison test, the limit comparison test. If you have questions, shoot me an email or I'll see you in class. Bye.